Hello, dear classmates. Welcome to the VLSI testing class. Today we are going to talk about an important ATPG algorithm, the D-algorithm. This is the outline. We will first introduce the D-Algebra. The D-Algebra is a 5-value logic which has logic 1, logic 0, and most interestingly, the logic symbol D represents 1/0, which means that the logic value is 1 in the good circuit and 0 in the faulty circuit. And similarly, D prime or D bar represents 0/1, which means the logic value is 0 in the fault-free circuit and 1 in the faulty circuit. The last logic value X represents not yet specified in ATPG. For example, the complement of D is D prime for an inverter. And here is a 2-input AND gate truth table. If both the inputs are D, then the output is also D, which means 1/0. We can see from this truth table. An interesting result is that when one of the input is D, the other input is D prime, the output will be 0/0, which represents 0. We can also see from the truth table. In the D-algorithm, we have two important components, the J frontier and the D frontier. The D frontier and the J frontier. The D frontier means a set of gates whose output value is currently unknown, X. But this gate has one or more D or D prime at its input. The definition of J frontier is a set of gates whose output value is already assigned, but its corresponding input values have not been decided yet. In this example, we can see blue gates belong to the D frontier. And the green gates belong to the J frontier. The output value has been assigned, but the input has not been assigned yet. So, the idea of D-algorithm is very simple. First, we try to activate the fault and create D frontier, like this blue line. And we try to drive this D frontier toward the output. This is fault effect propagation. And then we try to justify those gates in the J frontier. If there is any conflict in this process, we will backtrack. Let's show you an D-algorithm example. Suppose we want to test this stuck at 04. So we can activate the for by assigning both A and B to 1. So we now have a D generated at the output of gate G1. If we want to propagate this D through gate G3, we can assign the output of G2 to be 0. For the output of G2 to be 0, all the inputs must be 1. So now we know that C and E are both 1. This is called what we call backward implication. Starting from the previous slide, now we have two D frontiers. One is G5, the other one is G6. They both have a D at the input and their outputs are still unknown. So we can choose either one of them to propagate the for effect. Let's say we choose G5 to propagate to the output. So now we must assign the output of G4 to be 1. In that case, we can successfully propagate the for effect to the output and generate the test pattern. After this simple D-algorithm example, we would like to show you all the types of cubes that we need to use in the D-algorithm. First of all, we would need a primitive D-cube for fault activation. A primitive D-cube for a fault, or PDCF, means that the minimum input assignment that we need to apply to a gate input to produce a D or D prime and a gate output. For example, suppose we want to activate stuck at 0 fault at the AND gate output. We will need both inputs to be 1. Alternatively, if we want to activate a stuck at 1 fault at the AND gate output, we have two choices. We can either have 0x or x0. They are both primitive D-cube for this fault. A singular curve denoted SC means the minimum gate input assignment for gate output to be 0 or 1. For example, for the output of a 2-input AND gate to be 1, we would need both inputs to be 1. However, if we want the output F to be 0, we could have two choices, either 0x or x0. The same thing happened to an OR gate. For the output to be 0, we need both A and B to be 0. For the output to be 1, we could have 1x or x1. So for this circuit, we show different cubes in this circuit. The primitive D-cube for the fault G1 output stuck at 0 fault. We have AB equal to 1, 1 and G1 equal to D. And we also showed singular curves of G2, G3, G4, G5, and G6. A propagation D-cube or PDC is the minimum gate input assignment required to propagate a D or D' from gate input to its gate output. This is very useful in D-drive or implication. We will talk about them later. Let's see an example. Suppose we have a 2-input AND gate. To propagate the D from gate input to gate output, we will need a 1 in the side input. Or alternatively, we could have 2 Ds at the gate input. For an 2-input NOR gate, if we want to propagate a D from input to output, we will need a 0 in the side input. Also, the output will be complement, which is D'. Alternatively, we could have 2 Ds at the gate input to generate a D' at the gate output. A D-drive selects a gate in the D frontier and tries to propagate D or D' from gate input to gate output. So suppose gate G is a D frontier and we would like to perform D-drive. So this is our original old D frontier before D-drive. We assign the side input B to be 1 and we would propagate this D from input A to output C. So now we have 2 new D frontiers. When we do the D-drive, we need to use the propagation D-cube. During the D-algorithm process, we would sometimes need implication and sometimes we will need justification. We have 2 types of implication. One is called forward implication. Forward implication means that partially or fully specified input values can uniquely determine the output value. For example, for this 2-input AND NOR gate, suppose one input is 1, which is a controlling value. After forward implication, the output value is 0. For another example, suppose one of the input is D, the other input is 1, and the output of this AND gate is D. These 2 cases are forward implication. For backward implication, we mean that knowing the output value and the sum of the input values, we can uniquely determine the unspecified input values. For example, for this 2-input NOR gate, if we want the output to be 1, then both of its two inputs must be 0. This is called backward implication. Also, suppose that we already have one input of an AND gate 1. The other input of an AND gate is 0. Then we can uniquely determine that the other input of this AND gate must be 0. This is also called a backward implication. Please note that implication means no choices. Justification means that we can find a valid input assignment to achieve the desired values needed. Suppose we have a fan-out free circuit. The justification can be done easily. Suppose we want a logic 1 at the output of a fan-out free circuit. We can easily backtrace from the output to the input. So now both these two inputs must be 1. We can trace one more stage from here to any one of the gate input. And then we know that both A and B are 1. And C, E are don't care. F is 1. And we finish the justification easily. During this process, there is no decision needed, so we can always find an answer if it exists. However, for circuits with fan-out branches, then things are more complicated. We may or may not justify a line successfully. Suppose we have the upper case. Suppose we want a 1 here and we want a 0 here. We already know that one of the input is 1, the other input is 0. Then we have a conflict here. We cannot find a logic value for this signal, so the justification fails. For the lower cases, however, if we want a 0 here and we want a 1 here, we can easily find a solution to justify this value. So now we see the flowchart of the D-algorithm. During the D-algorithm, we try to keep a test cube, which is a partially specified Boolean values for testing a fault. In the D-algorithm, a test cube contains not only the primary inputs but also the internal logic values. The notation we use in this lecture is TCN, which means the test cube at ATPG step N. When we have more than one cube, we can try to intersect these two cubes. 2 bits has intersection if their logic values are not conflicting. 2 test cubes has intersection if there is no confliction in any bit. For example, 0 and 0 are not conflicting. 1 and 0 is conflicting. In this table, empty boxes means there is no intersection. Here is the flowchart of the D-algorithm. At the beginning, we are given a fault, and then we choose a primitive D-Cube, PDCF, to activate the fault. Let's call it TC0. After that, we try to find a propagation D-Cube and take the intersection of our existing test cube, and we perform implication. If the implication has no conflict, that means everything is consistent, then we check if there is any D or D prime that reach the primary output. If so, then we can move on to line justification. If we succeed, then the test is generated. During this process, if there is any conflict occurs, then we would need backtrack. We can backtrack to our last decision. For example, we can backtrack to our PDCF. If there is no D or D prime available at the primary output, then we move on to choose another gate from the D frontier, and we choose a propagation D-Cube, and we loop back to this stage to incrementally generate the next test cube. So this loop continues until we find a D or D prime that reaches the primary output. Now there is one more thing we haven't explained, which is the line justification. From here, we enter the line justification. First, we check if there is any gate in the J frontier which has not been justified. If there is no such gate, then we finish all the justification. Otherwise, we move down. For each unjustified line, we pick a singular curve and try to intersect the single curve with the test cube. If we can find a consistent answer, then we pick our next unjustified gate from the J frontier. This loop is repeated until every gate in the J frontier has been justified. If we cannot find any consistent justification, we will backtrack. So in this stage, we can backtrack to another singular curve. If there is no more backtrack to make, then the justification fails. When we run this D-algorithm, if there is any conflict occurs during the algorithm, we need to backtrack to our last decision, and we need to change our choice. The choices could be either primitive D-Cube, propagation D-Cube, singular curve, or the D-drive gate. Those are the decisions that we made during the ATPG progress. However, they are wrong decisions, so we need to backtrack those decisions. To avoid spending too much time on a particular for, user can specify a backtrack limit, which means the maximum number of backtracks allowed for a single for. If a particular for exceeds the backtrack limit, this for is aborted. For example, in this picture, the backtrack limit is set to 3. We have a conflict here, and also here. After that, we would not do any more backtrack, and the for is aborted. The aborted for can be detected. However, we cannot find it in the backtrack limit, so we will put it back to the for list. Here is another more complicated example for the D-Algebra. This is the same example where single pass test pattern generation failed. First of all, we generate the first test cube TC0 using the primitive D-Cube, where line input 2 and 3 are assigned to 1. So now we activate this for, and then we perform implication, but nothing happens. Now we have 2 D frontiers to choose from. One is gate G5, the other one is gate G6. Suppose we choose gate G5. We want to propagate this D prime through G5. So we would need a propagation D-Cube, and we assign input 1 to logic 1. After that, we can perform forward implication, since line 1 is already 1 and the line 3 is 1. So now we know signal 5 is now 0. Furthermore, we can also perform implication through G4. So the line 8 is now logic 1. Continued from the previous slide. Now we have 2 D frontiers to choose from. One is gate G8, the other one is gate G6. Suppose we choose to propagate to through G8. So we would need a propagation D-Cube like this, and we take this to intersect with test cube number 3. We will have this. We assign line 10 and 11 to be 1. Now we perform a backward implication through G7. We know that signal 7 should be 0. We also perform backward implication through G6. We know that line 4 must be 0. However, when we perform backward implication through G3, we see a conflict has occurred. Line 4 cannot be both 1 and 0 at the same time. So we need to backtrack. The last decision we made was in step number 6, where we chose the D frontier G8. This was a mistake. Now we backtrack to step number 6, starting from test cube number 3. This time we choose to propagate through gate G6. So we assign input 4 to be 1. And then we perform for implication. We get signal 7 is 0, and then we forward implicate through G7. We get signal 11 to be 1, and eventually we have the output to be D prime. There is no justification to be done, so the test is successfully generated, and the test cube is like this. So this example shows that the algorithm is a complete ATPG algorithm. We can find a test that failed the single path sensitization algorithm. So in conclusion, the algorithm is a complete ATPG algorithm that guaranteed to generate a test pattern for a testable form. However, as we can see, the search space of the algorithm is very large because we need to assign every internal signal, which is very time consuming. Backtracking can take place at each gate. This is very slow algorithm. So in the following, we will introduce an even faster ATPG algorithm called the potent algorithm. Now it's time for question. I have 2 questions for you. Question number 1. Why do we do justification at the end of the D algorithm? Why don't we just do it immediately after implication? Number 2. Please explain why the algorithm is a complete ATPG algorithm. Okay, thank you for listening. Bye bye.